Hello, Professor. My name is Raul Barrera, and I'll be solving question 8 of the final exam. Okay, so let's start. Now the question in the book. The question reads: a rectangular circuit is moved at a constant velocity of 3.0 meters square into throughout and then out of a uniform 1.0 magnetic field as shown in figure 2. The magnetic field region is considerably wider than a 50.0 centimeter. Find the magnitude and direction, clockwise and counterclockwise, of the current included in the circuit as it is. A is going to the magnetic field, B totally within the magnetic field but still moving, and C moving out of the magnetic field. Sketch a graph of the current in this circuit as a function of time, including presence of the three cases. Okay, so I pretty much have to gather all the three cases, get the magnetic direction, and do a graph. Okay, so let's start with identifying. We have to identify that there is change sorry in the magnetic flux produces in the induced EMF. So that's all we know. So now you have to set up the equation. So I will use a flux throughout. So it will be E equals over dt. So our induction current is given as EI equals E over R. Okay, now let's do that and execute it. So it will be part A. So we have a uniform magnetic field. B equals 1.25 t. Velocity is given as V equals 3.0 meters squared. Resistance is also given. R equals 12 points. Sorry about that. And then we're going to use it like this. We're converting. This will give us, so it'll be 0.75 meters. So as the circuit is going into the magnetic field, then inducing the EMF will be, so then when it's induced, you have to change the formula. If I remember correctly, that would be E equals BVL. Yeah. So the induced current is I equals BVL over R. So let's put this in the formula with what we're given is 1.25 T. 3.0 meters square, 0.75 meters over our resistance, which is 12.5. Then when we do the math, this should give us 0.225 amperes. So that's one of the parts that they're asking. So as the circuit is going into a field, then magnetic flux is increased in the direction out of the page, then included current should be clockwise. So current is included clockwise. So for part B, so as a circuit in the magnetic field and it's still moving, then change in magnetic flux is 0 and induced the current is 0. So yeah. As a circuit magnetic field and is still moving, then change the magnetic flux is 0 and induced current is 0. Very important. So now we're gonna find out, as the circuit is going out of the magnetic field, then induced it will be. So now we have to find out what the induced current is. Just put that as part C, for example. So we already know that E equals PVL, and then our L, which we already saw, is 75 centimeters given to us. So that our induced current is going to be PVL over R. And this will be the same formula we already used. This will be A equals 2.025A. So the same thing, as the circuit is going out of the field and the magnetic flux is decreasing in the direction of out of the page, and its induced current should be counterclockwise. So this should be counterclockwise. So I feel like the graph should be, well, this is I, then this is T, so we will have something like this, and then something like this, opposite. So here, positive and negative current represent the direction. So positive, negative represent the direction. This is not positive, this is T. Sorry. No, let's change. I can't do my T's, I'm sorry. There. So direction of induced current can be determined by using the Lenz's law. Then believe that this is the graph. We already figure out what's the current. Yeah, Professor. Hopefully I'm somewhere in the right direction. Thank you for your time. It's been a nice semester. Thank you, Professor.